Good morning. Good morning. So we have some distinguished experts on space weather and their impact on critical infrastructure on planet Earth. And it's my pleasure to introduce them. So our first speaker will be Bill Murtagh of NOAA. Bill was at the Space Weather Prediction Center out in Boulder, Colorado, and was it 2 years? A little over 2 years.
Felt like 10.
He felt like 10. He never got much time off, couldn't get back to Colorado as often as he should have, but he was a co-chair of the SWORM, the Space Weather Operations Research and Mitigation Task Force. It was co-chaired with Caitlin Durkovich in Homeland Security under the Obama administration, and they put out a major report, and it led to an executive order, a space weather action plan, and this is one of the executive orders that's still in effect, and the SWORM continues to operate, and Bill is a leading executive of that. Stephen Clark of the Office of Science and Technology Policy is coordinating it in the Executive Office of the President. So Bill will start, and then we're going to follow up with Professor Adam Schultz from Oregon State University. And Adam has been an expert on the geomagnetism modeling, geoelectric fields, doing work for the NSF Earthscope project, and they've been pioneering 3D modeling, which is not only relevant for solar storms, but may be important to understand the impacts of E3, the electromagnetic pulse effects on systems connected to long lines. And you heard earlier this morning Jordan Kearns talk about not protecting the entire grid, but trying to identify what critical assets especially need protection. So the gentleman here can provide insight not just about space weather, but also if we don't have the resources or we don't have the time to get our grid up to snuff so it works entirely, what are the critical modeling efforts, critical operational initiatives that can get us partway there? So I'll turn it over to Bill Murtagh.
Good morning, everybody. It's certainly a pleasure to be here. We are shifting gears a little bit. We are talking about a different enemy, not North Korea, but the sun, which of course is the provider of all things good in life as well, but it can do some pretty evil things, and we're trying to do something about that, or protecting ourselves against that. So what I'll do just here in the next 15 minutes is give you a quick update on the strategy and action plan that we've been working on at the White House. As Bill said, this new administration has embraced as many change. Really, we're still operating as we were at the end of the last administration and the implementation, so that's all good news. Just to back up before we jump into that, to remind everyone what we're talking about. When we're talking about mitigating the impacts of space weather, what are we talking about? We're talking about mitigating the impacts of 3 different types of emissions from the sun. The electromagnetic radiation, that speed of light, it only takes 8 minutes to get from the sun to the Earth. It affects the technology here on Earth. The energetic charged particles and how they can penetrate spacecraft or even cause aircraft to reroute away from polar routes because of radiation exposure or impacts on technology. And that last piece is the key piece, the magnetic field. An eruption from the sun, a coronal mass ejection, 1 billion tons of plasma gas that can erupt from the sun. It contains magnetic field. It's essentially the sun shooting a magnet out into space, sometimes right towards Earth. It makes that 93 million mile transit from sun to the Earth, and then we get an interaction. We've got 2 magnets, Earth's magnetic field and that magnet that got shot out of the sun coming together, and that impact can cause geomagnetic storms, disturbances that can be very significant to our technology. We've got a big magnetic field that protects the Earth for the most part, but it creates some of the problems too, the interaction of the two magnets, and even closer to Earth, the ionosphere. And the disturbances there can cause big problems to the technology we rely on as well. Emphasis on the magnetic field piece and the impacts on the electric power grid. These coronal mass ejections, they hit the Earth, the fluctuations in the electric fields are created above us, and are manifested here on the ground in the form of induced currents, unwanted currents that gets right into big conductors, like railways, like pipelines, but most importantly, the interconnected big electric power grid. And the bad news story, as we look closely at this over the last decade, is one of the most vulnerable areas in the world to this geomagnetically induced current problem is right here in North America, most specifically the corridor between Washington, D.C. and New York City. So it was an important message in the White House that, if we were to lose power in this vulnerable area in the Northeast for an extended period, the consequence could be very significant. Briefly, why are we more vulnerable up here? Largely because of the latitude, the higher latitude, our proximity to a large body of conductive material, salt water, the ocean. Also, the conductive material beneath us, the geology. That Adam was actually going to be talking a little bit about that here in a little bit. That plays big time into the vulnerability, and of course, having that interconnected grid in this upper part of the country all contribute to making this a more vulnerable area. I always like to point out, we talk about extreme events a lot, or in the man-made EMP, we talk about something that could happen, and in the natural EMP, we often talk about this extreme event that could happen, but recognize this, the space weather happens all the time. The Space Weather Center operating 24/7 in Boulder, Colorado is issuing alerts and warnings every week. And I just wanted to highlight a couple of examples. November 2015, I like to show this one. A lot of people don't realize this happened. In November 2015, a moderate level eruption on the sun shut down the airspace over Sweden. The air traffic controllers there were working fine, everything's hunky-dory, and all of a sudden their radars, the scopes they're watching had all sorts of interference, and they had to shut down the airspace. I was at the White House at the time, and the question was asked, and wasn't it a good question? It was asked, Bill, can that happen here? Could that happen and shut down LaGuardia and Kennedy, Newark? If it does, what's the consequence? We know the consequence is going to be very, very significant. Unfortunately, we don't really know the answer. It's part of the strategy and action plan is to find the answers to these kind of questions, assess the vulnerability of the critical infrastructure. In September, so this is just a couple of months ago, again, just to remind people this happens all the time, you can see the image of the sun there. We had that nice big flare on the right-hand side of the sun. On our X-ray plot, you'll see orders of magnitude on the log scale increase of X-ray emissions that we're feeling right here on Earth. And that's what it does. That whole area you see in red is the high frequency communication impact. When you see red, that's bad. That's loss of HF communication capability. Happened at a bad time. Recognize the date here, September. What were we dealing with in September? A whole series of hurricanes. And that's one of our worst case scenarios is that we get we talk about a space weather event creating the emergency, should it bring the grid down, but we could also have space weather events that interfere with our capability to respond to an emergency created by some other natural or man-made phenomena. These are the kind of reports that came into us from the weather unit supporting the aviation down in Florida. They said all the chaos of Hurricane Irma hitting South Florida and Jose impacting the eastern shore of the Miami airspace, a major solar flare occurred, disrupting communications of airplanes trying to fly in that whole area. So it created quite a bit of chaos for periods of time, these solar flares and communication. Also, this came in from the Hurricane WatchNet. He said, I'm not sure how long this blackout will last, but these flares could not happen at a worse time. We're looking at 3 hurricanes threatening, and we cannot make contact with anyone on these frequency bands. So it's just an example. We're working with people all the time on space weather because it happens all the time. Now, as the biggest part of our strategy to mitigate against space weather was to develop a strategy to get top-down support to address this issue. For decades, I've been in this business for decades, it was a bottom-up approach. It wasn't working. We were having some successes, given due credit to the folks that were involved in getting things done over the decades. What we needed was support from above. We got it in the summer of 2014 when the President and his senior advisors wanted to see some kind of cohesive national strategy to address this issue of space weather, recognizing that the DHS and FERC and DOE and others were doing great work, but what was lacking was that strategy, that cohesive strategy. So in November 2014, the Operations Research Mitigation Task Force was established at the White House, and in October 2015, the strategy and action plan, just 1 year later, was released. Strategy is just that. It's a simple enough document, 12 pages, designed so that a budget analyst, others with non-technical backgrounds can read and understand the issues. And then the action plan provided the meat and potatoes, if you will. That would be the actions necessary to build resilience in this nation against space weather. Who's responsible? Which federal agencies own this problem? And of course, a timeline to implement. The strategy and action plan was good, but we needed more. We needed the hammer, I often say. We needed some kind of legal action to make it, to put the force of law on it. We had opportunities either to pursue legislation or pursue executive activity. As it turns out, we went both directions. We had success then in October of 2016, so just a year ago, with the President signed Executive Order 13744, coordinating efforts to prepare the nation for space weather events. One key thing it did was this. It developed a subcommittee at the White House responsible for the oversight of implementation of the action plan and the actions contained within the executive order. In other words, the ownership would be at the highest level within the White House, and it continues there. And next Thursday, the 7th of December, will be our next. We meet quarterly at the White House to discuss progress on the implementation plan. This is also very important that the legislative side of the House went after the issue as well, recognizing that there is some vulnerability to executive orders, as we know. We wanted to put legislation on it. The Senate passed Senate Bill 141 on the 2nd of May, unanimously with support, of course, both sides of the House. So that was very important. And then the House introduced a companion bill in June of this year. So it's been assessed and evaluated right now. But it's a Research and Forecasting Act. But I did want to pull out just a little bit of language to show you it's a lot more than that, than just the research and forecasting. You'll see the Secretary of DHS assess the vulnerability of critical infrastructure. The National Security Council assess vulnerability of the national security community, develop national security mechanisms to protect against these space weather events, and the FAA assess methods to mitigate safety implementations and effects of space weather. So recognize if this bill does pass, it will be a significant step forward in our efforts to provide the governance over the building resilience against space weather. And I just wanted to touch on a couple of the successes of our action plan. The benchmark piece was very important. What was lacking, one of the things that was lacking, was we didn't have a good sense for how big is big on a space weather event. How can we talk to industry, whatever industry, and say you've got to protect against this threat if we don't tell them the level of the threat? So we're in the process of defining the benchmarks. We've brought the science community across this country, both private sector and government, to work on this issue. Phase 1 is going to be released here this month. And it's going to be essentially a rather brief effort to identify these benchmarks. The Phase 2 initiative is going to be much more involved, and we'll actually coordinate with the international community to do that over the course of the next couple of years. Some of the other things that are happening, and Adam's going to talk about this, but the magnetotelluric survey, the MT surveys, we wanted to understand that ground conductivity I mentioned, to understand better how the induced current might flow. These guys have been doing great work on developing and understanding the magnetotelluric survey and doing that survey across the nation, but there's big gaps. One of the big gaps was the important area, the Northeast. Well, we worked with the SWORM initiative, and the task force got together and we quickly came up with $500,000 to complete that, and these guys just finished that just this month, I think, was it? Yeah. So that whole northeast sector is done. Now we're working to get the rest of the country done, the last third of it. So good progress there. I also wanted to mention that commerce, we wanted to do some kind of an assessment of the economic impact. Leadership always want to understand that. So Commerce let out a contract to the Apt Associates, and that report will be released here before this month, essentially before the end of 2017. That's going to be very valuable in our efforts. We're also going to conduct a comprehensive survey of the requirements. What is it? Because if I'm going to work with the power grid, they say I have to ask them, maybe it's Con Ed in New York City, what do you guys need? How much lead time? What level of accuracy so you can take the right action? We need to define those requirements. We're in the process of doing that now. We just let this contract out to Apt Associates, so it's another big step forward. This is interesting too, and I was very pleased that this is happening because it's a great example of government working with private sector. This is largely in support of GPS and the ionospheric disturbances. It's what we're called radio occultation. We take measurements from land. What about the ionosphere over the other 2/3 of this Earth, or the ocean? Well, what we're doing is we're going to do radio occultation, where we're going to put satellites in space and send signals to the GPS that essentially goes through the ionosphere and helps us capture what the ionosphere looks like. Now, this is not a plan. This is happening. The contract was laid out, and that group called Spire have 7 satellites up there, and in the next coming months, these are little CubeSats. We're going to have a couple of dozen of these satellites up there doing this. This is going to be a huge step forward in understanding the ionosphere and providing the services necessary to the GPS, which of course pervades society today. So I just wanted to touch on a couple of key things. Obviously, the first part, everyone in this room knows about the importance, the vulnerability because of the interconnectivity and the interdependency of our systems. We've created an incredible vulnerability. Should we lose any of these critical technologies, the consequence is going to be so significant. I want you to understand that the new administration has embraced the issue, and we continue the federally coordinated approach to develop the policies and practices and implement the action plan. And that last piece, of course, we can't go it alone, and I used that last example with the company Spire to demonstrate we're working too with the private sector to make sure that we're doing what's necessary to get to where we need to be to build resilience in this nation against the threat of space weather. Thank you.
Bring up my talk, I'd appreciate it. So while we're waiting for that, there we go. I'm going to use one of the privileges of an academic, I think, and that is to look at a complicated problem and maybe step back from it a little bit, look at some of the risk assessments, and really go to first principles and see if there are any underlying assumptions that may have gone into them that may be better or less supported by the latest scientific research. And some of that is some of the research that Bill just alluded to. I'm kind of struck by the need to do this ahead of disaster. A great example of doing this in retrospect was Challenger. I mean, most people in the room are old enough to remember that news conference where the famous physicist Richard Feynman got a piece of O-ring material from Morton thiokol, put it in a glass of ice water, pulled it out, and snapped it in two. Right? That's a problem with some of the underlying assumptions that went into the engineering analysis of risk with those solid rocket boosters. So let's not have that happen in the grid. And most people have seen this diagram a million times from the EMP Commission reports. And we see basically the gross interdependency of all aspects of critical infrastructure on which we depend. And if there are any critical points of failure, there's a cascading failure across all of these different bits of critical infrastructure. from the perspective of space weather that you've just heard from Bill, we have a point of contact between space weather and this entire network of interdependencies that runs through the Earth. The physics of the Earth now gets involved. And so I'll talk about that and some of the underlying assumptions that go into the risk assessments. Similarly for EMPs, and particularly as you heard several times today, the long time phase, the E3 phase of the EMPs, similarly interact with this network of interdependencies through the Earth. It's the Earth connectivity structure. Of course, the E1 and E2 phases directly impact most of these. The E3 phase gets filtered through the Earth. And just as an aside, it strikes me when we look at the various risk analyses, usually we consider them in isolation. It's what would one EMP do? But why would a hostile actor launch only one EMP during a coordinated attack? Why wouldn't they also coordinate with a cyber attack at the same time? You can just see the layering to make each attack more successful. And again, I don't need to beat a dead horse. Plenty of people have done this already. Our thoughts are now rather focused on the issue of E3 phases of EMP as well as the space weather phases for all of the obvious reasons. Okay, now in order, the threat here to the power grid is GICs, geomagnetically induced currents caused by space weather. In order to predict the intensity of the GICs on the grid, which is the thing that leads to, for instance, reactive power loss on the transformers that can bring the transformers down, lead to cascading failure modes, and bring grids down, you need to accurately predict in real time the intensity and direction of the electric field at ground level anywhere near the grid infrastructure. The electric field and the magnetic field are vector fields. They have both an intensity and a direction, and that intensity and direction is constantly changing. So during a GMD, a geomagnetic disturbance, a space weather event, there are low frequency magnetic field time variations, and what they do is they diffuse into the Earth, they induce electric currents to flow through a wide and deep volume of the crust and mantle, and they have a frequency content. So higher frequency variations of the magnetic fields due to a GMD don't penetrate as deeply as do low frequency variations. So you can think of the frequency of these oscillations as a proxy for depth of penetration into the Earth. Each geomagnetic disturbance has a different signature because the magnitude and orientation of the magnetic field associated with that will be different from one, the time progression will be different from one GMD to another. So you can't base your risk analysis on just a single GMD. You have to look at a whole range of different scenarios. Now, here's the fundamental assumption that I'm going to really focus on today that goes into essentially all the risk assessments done to date. If the conductivity of ground, and by ground I mean this below the Earth's surface, the crust up shallow and then the mantle below, if it varies only with depth, we call that the 1D assumption, if it varies only with depth, it turns out some physics happens. The electric field that's induced in such an Earth is always at a right angle to the magnetic field. Okay, that's the first thing. And the orientation of the magnetic field doesn't matter. You'll always get the same magnitude electric field out no matter what the orientation of the magnetic field is for a given magnitude of magnetic field. That's what happens in 1D. But if we get away from that, say the real world is 3D, we know it is. If the conductivity varies in 3D, it turns out the horizontal electric field can point in any direction relative to the magnetic field. And as the magnetic field rotates, the relative orientation of the electric field can change radically. And its magnitude can change even if the magnitude of the magnetic field doesn't change. So the behavior is totally different in 3D. And it turns out no matter how finely you divide the continental US up into little regions where you consider only 1D solutions to this problem, you can never reproduce that behavior because the electric field is always going to be at right angles to the magnetic field, and it's always going to be independent of the orientation of the magnetic field. So that's a fundamental thing. To help clarify what I mean by 3D and 1D and all the rest, on the left you consider a cube I've cut out of the Earth, and I've plunked on the screen there. So you see the top surface of that in red and blue, and then there's a vertical section with depth. The top bit is the Earth's crust, and the upper mantle below it. And this is showing the spatial variations in electrical conductivity or electrical resistivity in this 3D volume. And this is kind of a real-world scenario. And red is very conductive, electrically conductive. The blue is very resistive. And in this particular image, there may be 3 or 4 orders of magnitude variation in this property, the electrical conductivity, as you move laterally in any direction at any depth. For the 1D world, you've turned it into a bunch of horizontal pancakes layered on top of each other. Each pancake has uniform conductivity. That's kind of what's used by the industry and standards right now, generally, 1D. Or you get this kind of hybrid model where you've divided the country up into regions, but inside of each region, you pretend it's 1D. That's actually a physical impossibility. The equations get broken when you do that, but that's what's done. Because the horizontal extent of each of these layers goes to infinity. It's true for that right model too. So you have all these infinitely big things somehow having to fit together in a finite space. So the equations get broken. Okay. So I think this leads to an under-recognized vulnerability in the existing assessments of risk to critical infrastructure, because the current assessments for GIC and for HEMP E3 impacts follow the NERC TPL 0701 standard, and they simplify the electrical conductivity structure at every point on the Earth's surface to be that of a one-dimensional Earth pancake model. And it turns out that's based on information that runs counter to modern observations. We know that's not true. We have the data to show that now. And it has a profound impact on the intensity and direction of ground electric fields, and then downstream that affects the intensity of the GICs and how it loads the different transformers on a grid. How we actually collect the data very quickly, we use the magnetotelluric method as Bill indicated, and on the right it's just a schematic diagram showing we measure the Earth's electric field by planting electrodes and measuring voltages. We measure the Earth's magnetic field by magnetometers in one place, and we'll operate these observations, collecting data over time for a long enough period of time to get us information we need for a particular target depth. And it depends on the project we're doing how long we may sit there. It may be a couple of days, it may be 3 weeks, it may be months or more. And then on the left, just an illustration of one of my students collecting MT data at Mount Rainier in Washington State. Okay, so in order to do this, we've built up at Oregon State University the National Geoelectromagnetic Facility. We got some stimulus money in '09 to help nucleate this. And we currently have the world's largest collection of MT equipment. There are very few people in the US who actually use this method. It's used hugely in places like China and Europe. The US has very little expertise in this, unfortunately. And so it's kind of a sad statement that such a small facility is the biggest one in the world. Most people have, a couple of these instruments. But this is what we need to do the sort of work that Bill's shown you. So I'm the principal scientist for the NSF supported Earthscope magnetotelluric program. These dots on the map show sites we've completed. You've seen this from Bill. I've added some dots from 2017 in the upper northern Great Plains, and we're fleshing that out for 2018, at which point the Earthscope funding ends. Earthscope's been a long-running program, and it simply ends this fiscal year. But during the time we've been doing this, we've been collecting long-period data of the sort we need to look at the Earth's mid-crust to upper mantle. That's good for GICs in the power grid. And also, we've done some higher frequency, finer scale work that's useful for looking at the upper crust, which is useful for the E3 phase of EMPs. And all told, we've collected around 1,000 stations of the long period kind on this regular grid, and about half as many in finer scales like in the Pacific Northwest. Keep in mind, this work was never motivated by power industry concerns or GICs. This was a basic research program in the solid Earth to look at structure and evolution of the North American continent. When we set out to plan this 15 years ago, we had no idea there'd be an application like this. It's one of those scientific serendipities that happen. Now, just to illustrate the problem, if you use the current standards for risk assessment, North America has been divided up into these regions. That's the map on the right, these physiographic provinces where inside any one of these zones, the connectivity is taken to vary only with depth. It's the 1D pancake model. Well, there aren't that many zones in this northwest quadrant of the US. If we look, for example, through one of our 3D images of the electrical conductivity structure for real, based on the Earthscope data, this is a slice at 31 to 37 kilometers below ground level. look at the degree of variability, again, around 3 orders of magnitude variability, and if you look and try to stare and compare with any one of those supposed geoelectric regions, you still see about 3 orders of magnitude variability everywhere. So it's nothing like the 1D scenario. And that's true at every depth. If we go on a much finer scale, if you look on the right side, there's this region PB1. It's the Pacific Coastal region that's running from much of California up through the Pacific Northwest until you get up to Puget Sound in Washington State. And that's electrical resistivity at a depth just within the PB1 region using a finer scale data set. So even on this really fine scale within a single region that's supposed to be uniform, it's nothing like. Okay. Now, I like showing this because in a lot of the work, when you go to things like the GMD task force, people are showing model-based results, and you always wonder how valid are the models. I thought I'd just show you some data. So this is data from the Oregon coastal region, from the Cascade volcanoes on the east side of each of these figures to the Oregon coast on the left, Pacific Ocean on the left. The one on the right and the one on the left are basically in the same place. It's a slight blow up of the region on the right, but it's more or less the same piece of coastline. You're looking at temporary arrays of magnetotelluric equipment that were running in 2013. These are 2 different days, July 4th, 2013 on the left, April 25th, 2013 on the right. The reason you're seeing these vectors, and I'll explain them in a second, in different locations is we don't have all this equipment in this big area running simultaneously. We have so many instruments, we put them out, we move them. It's a moving roadshow. So on that day, we had that equipment running. On that day, we had that equipment running. What I'm displaying now is actual data averaged for 1 minute. So these are 1-minute mean samples of the magnetic field is actually recorded, and the Earth's electric field is actually recorded. The magnetic fields are in red, the electric fields are in white. If the Earth is 1D, as it should be in this PB1 region used for risk analysis, the electric and magnetic field should always be at right angles. And if there's a small rotation of the magnetic field, we shouldn't expect to see any big change in the intensity of the electric field, and we see quite radically different behavior. So this, again, is kind of a case where I'm not trying to sell you a model. This is what the data is showing us. Again, this isn't just a West Coast phenomenon. We've done this along the eastern seaboard. Same story. We've done this in the mid-continent. Here we are in the northern Midwest. And if you look at this IP3 central lowland region, that's the reality of our heterogeneous 3D structure. So Houston, we have a problem, right? So we've developed some algorithms that make use of this Earthscope and related magnetotelluric instrumentation in order to see if we can predict what the electric fields really will be from a 3-dimensional Earth. And we found a very efficient way of doing that. And I can't go into the details, but what I can show you, for example, is just a quick slice through huge analyses. This is for a station, happens to be in the BPA operating area near Portland, Oregon. You're looking at on top the northern pointing component of the Earth's electric field, and the bottom, the eastward pointing component of the Earth's electric field. It's a vector field. It has a direction. And in green is data actually measured. That's a time variation of the Earth's electric field at that site is actually measured. And using our prediction, which uses as input, in this case, U.S. Geological Survey magnetic observatory data from distant locations, goes through a series of filters we've created. The red is a predicted electric field. And that makes use of the 3D ground conductivity information. And we can show plenty of examples where the 1D assumption doesn't predict the data anywhere near as well as the 3D prediction does. If we look at another way and we map it out over broad regions, we can ask, how important is the 3D effect? If this was a 1D chunk of Earth, we would have a uniform color here. This is the amplification of the electric field due to 3D effects. And we see over this region, we have electric field varying from a single GMD anywhere from 0.3 millivolts per kilometer all the way to 107. That's due to 3D effects. It's not a single number. It varies over 3 orders of magnitude or more. Okay. Or if you want to look at it in vector form, this is quite interesting. This is during an actual GMD in May 2016. It represents the average intensity and orientation of the Earth's electric field over a 3-minute long window. And we're looking at the 1D industry standard way of doing risk assessment are the white arrows. And this actually represents a number of those 1D regions. So the white arrows have different sizes depending on what region you're in. And the red arrows are the ones that come from the 3D response. And again, that illustrates what a big difference 3D is really making. And then to make this useful, you integrate along the power line paths, you plug it into a power flow simulation of the power grid, and you can look at the reactive power loss on transformers. And that's what this image is. I'm not going to go into any of the details. It's actually screenshots from a user interface from one of the industry standard power flow tools that power companies use called PowerWorld. But what we do is take the real-time ground electric field predictions, we project them onto the path of the power lines, we integrate along the power lines and plug that into a simulator that has the electrical properties of the grid, and we can actually look at the impact on the grid of this. Okay, so moving toward the end here, what conclusions can we draw from power flow simulations where we have a 1D standard way of doing risk assessment and the 3D cases, and this is for a particular power line running through Bonneville Power Administration territory. It's an east-west power line. And it turns out that different parts of the line experience different electric fields for the 3D real-world case, but they would see the same electric field in the 1D case. And at the start of a particular GMD event in this case, we show the calculated electric field intensities at two substations. One's on the east end of this transmission system, the other's on the western end of the transmission system. And we see for the 3D real-world case, we got a huge variation in electric fields. That's the top row of this little spreadsheet. And on the bottom, the 1D case is uniform. It doesn't matter what substation you're at, and it's a very different value. So that has a real-world impact. In fact, if we look at now the reactive power loss that you see from the 3D versus 1D case, it's kind of an interesting phenomenon. First of all, they're different, right? We get 0.025 mVAR for the 3D case, and only you get a bigger one, 0.04 mVAR for the 1D case. But it's kind of interesting. If you compare the electric field that the two substations are seeing, it's actually much bigger for the 3D case. But the reactive power loss is much lower for the 3D case, which seems to be a contradiction. Why? We're actually looking at a blow-up. This is the power transmission line we studied. It's that little black line there. It's running toward the coast. And there's an eastern substation and a western substation. The one-dimensional, standard way of doing the risk assessment has the electric field during the start of this GMD pointing this way. The 3D has it rotated for the eastern substation. It's at a right angle to the power line. It contributes no GIC to that power line. It's not pointing in the right direction. The 1D solution has a little component pointing in that direction, so it gets a bigger reactive power loss than the 3D. It's the opposite situation at the other end. So direction matters, and that changes over time. So if you base a risk assessment on a 1D solution and you don't factor in these 3D effects, what you end up with is, for any individual transformer, the possibility that you've either overestimated the risk, and a power company is going to have to pay a lot of money to protect the transformer that may not need protecting, or you've underprotected. And that's equally true for EMP. Okay. And that's true of everywhere we've looked. So I'll just say, in summary to this, before I get to my wrap-up, these effects can't be reproduced by replacing the 3D real-world data we're now getting out of this NSF-funded project with a set of 1D models. Where do we go? Well, Bill's indicated that there's a priority here somehow to fill this gap. These are all the stations that Oregon State Universities obtained with NSF funding, with some fill-in by the U.S. Geological Survey in yellow there, in Florida and in the southeast. But we have a big gap in areas of very important critical infrastructure. We also need to take the data and analyses and bring it to a practical use. So we've received funding from the National Science Foundation, partnered with a data mining company called Ping Things that has access to synchrophasers and neutral ground return current information from various power grids, and also several power grid operators to provide a new smart service system that the power companies can use that will give them real-time assessment of reactive power loss based on data streaming in from all of these different systems. So I'd like to thank our support, and I don't know if there's time for questions, but I'd be happy to answer any.
we'll take a few questions. I just have one for both of them first, which is the Defense Threat Reduction Agency is developing expert systems to help electric utilities input their systems to understand where they might protect against EMP. And I'm asking, I think I know the answer, but I want to hear it from you. If they don't have the 3D data in it yet, so what do you think this, Adam, for the specifics on the 3D and Bill for more general assessments? How close are we to be able to improve these expert systems that will soon be available to the electric utility industry by bringing in the science that's been developed from solar storm research?
Yeah, so Bill, one of the big developments here is the aim here, of course, is to produce a product that describes, identifies the E-field. Working for years, and I know there's folks, Frank Coase and some others are out there, power companies have relied on magnetic field values to take action, the K values or other types of values that essentially identify disturbances in the magnetic field. We want to actually get to the next level. The next level is, of course, the electric field that's generated, and people like Adam are even taking it to, so the government, we've actually produced at NOAA an E-field product that's in test mode right now. We're working with electric power grid companies on the validation of that model. At the same time, it's the kind of thing we like to see, private sector, academia, like Adam, are working on something similar, and even taking it further, as he mentioned, where not only do we have to understand the E-field, but the induced current and the local impacts on technology. So there's great things happening, Bill, that's why I believe that gap drives me crazy, that we can't get, this is, we're talking about chump change here, maybe $3 to $4 million to complete the magnetotelluric survey for this country, and the cost benefit here is incredible. The importance of finishing this information. The meeting at the White House next Thursday, as I mentioned, it'll be front and center, this issue, and I expect results. I'll say with some degree of confidence right now.
Yeah, thanks. I think we are getting quite close. I mean, I'm not criticizing anything that's gone on before. People use the best available information, and there's always a time lag between what scientists may be doing in their lab and what then gets filtered down and used by regulatory agencies and other groups. And one thing we've been trying to do is close that gap and make the communication channels better, because we're too compartmentalized. And that's actually happening. It's happening at the NERC level, it's happening at the FERC level, it's happening at the interagency level, because we all recognize the severity of the issue. And also the cost of mitigating it. And one of my pet peeves is we don't want to overprotect either, because it's going to cost, I pay 8.4 cents a kilowatt hour in Oregon. I kind of like that, and I'd rather not see my power bills get jacked up because things have been overprotected as well. So it's getting the balance right, and also getting it done in a time frame that's meaningful. First time we showed these maps of the station locations, and I said what the entire, I think we spent maybe $12 million over a dozen years getting every one of those dots. And somebody thought I said billion, and they didn't seem to think that was a lot. So this is a really trivial thing to do. It's just a matter of deciding how to do it.
So we'll just take one question from the floor. George, let's get you a microphone.
I got it.
Yeah, very important work. And now I have a question. There's been a lot of conjecture about Neumann boundary conditions along the coast, where you could get very large field enhancements because of the water, the edge of the water enhancing the field. How big might that effect be, and are you looking at that?
Oh, absolutely. So this is long known as the coast effect for people who do magnetotellurics. And back when we were stuck in doing one-dimensional worlds ourselves, the thing that really ruined your day was the fact that you were anywhere near a coastline and clearly 1D was broken there, right? So that was the coast effect. But now that we've mapped the interior of the continents, we see just as big a variation in conductivity interior as you do at the coast. So there's like a coast effect everywhere, and it's just the fact that the Earth is 3D. So you got a big, enormous seawater conducting deep thing next to a resistive continent, you get a conductivity contrast, it's a 3D effect, just like it is anywhere else.
How big is the field enhancement?
It's quite large. I mean, we see orders of magnitude in some scenarios, changes in the intensity of the electric field. But also, it's not just the intensity, it's the direction. And that matters when you're looking along a power line.
And that would apply to the coast as well?
Absolutely. Yeah.
So we want to thank our panelists for giving us this new research insight. Thank you.